we are going to go through how to handle a kinematics problem, namely a problem that involves using these equations. You should have those handy at all times while doing these. It is extremely important that what you pay attention to here is not the answer, is how I set up the problem. Because when I grade these things, when the AP people will grade these problems, there's certain things they're looking for. And while this problem is pretty easy, the things that I am talking about are important, not how easy this problem is. I cannot stress this enough. If you got bit by it last chapter, when we were doing forces, be aware that how the problem is done is as important, if not more important, than the answer. Way more important, actually. Okay, so we will start with, first thing I want you to do when you get a kinematics problem, there are 6 quantities. 3 that change. So for example, your position, your final velocity, and time all change. And in fact, let me write them. Put those 3 last. And there's 3 quantities that, from the outside of the problem, are the same. They're kind of your defining characteristics. So they would be your original position, your original velocity, and your acceleration. So I'd rate those 6. The order really doesn't matter, but I like doing them in that order. So these are sort of the things that come with the problem, or I may have to find them, but they're initial conditions. These depend on time. But those 6 things with equal signs next to them need to be in a problem. If you come to me for help and I don't see that, I'm not helping you, because that's how I'm going to look to determine if you're getting the physics of it or not. So let's go, then we check the problem and we look at it to see what we have and what we don't have. So really this is an exercise in mathematical problem solving and reading a problem. Not, the physics is actually less than in the previous chapter. So a motorcycle has a constant acceleration of this. So they've given me the acceleration. If they don't say it explicitly, remember, these are the units for acceleration. So that must be what it is. We're dealing with a horizontal problem, so we don't have to worry about g in this case. This is all in the x, or the horizontal. So I have 3.84 meters per second squared. Now the physics says, let's check to make sure the sign is correct, like the direction. And they say both the velocity and the acceleration of the motorcycle point in the same direction. Okay, so the initial velocity and the acceleration point in the same direction. If they pointed in different directions, I would make one positive, one negative. Here, I have a choice of making them both positive or both negative. Obviously, both positive makes more sense, but it's important to note that you could make them both negative and the problem would work out still. Okay, so then how much time is required to go from this speed to this speed? So we have 2 velocities. We have the initial velocity and the velocity at some later time. So I fill those in. So the later time velocity is 49 meters per second. And the final velocity time is going to be 39. Did I get that right? No, the initial is 39. There we go. Meters per second. And the final is 49 meters per second. And then I will tell you that in most of the, I'll say 90%, I'll make up a number, but the vast majority of horizontal motion problems are going to be done in such a way that we can call the beginning position 0. We'll just say wherever he starts, when we start the stopwatch, they're going to call that 0 meters. So this leads us to having filled out this thing with everything but 2 items. This is important. So you're generally going to get it down to 2 things that are missing. One of them is the thing you're looking for. And the other one is going to be the thing you don't care about at all. They're not asking you for it. They don't give it to you. So these right now, the thing you don't care about. So which one is which? If you read the problem carefully, what are they asking for? They're asking for how much time. So this is our target. This right here, let me get an arrow. Boom, 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 boom. This, in this case, is the thing I don't care about. And actually, that turns out to be important for us, because that's how I'm going to pick these equations. Which equation to use, I should say. Because I don't want an equation with x. Why? I don't care about this value. I don't give it to me. So so x, anything with an x is not something I want to use. Well, here's an x here. There's an x there. Wait a second. This one doesn't have an x. So did you catch that process? You carefully list these things out. You'll probably have two unknowns. One of them you don't care about. One of them you do. Use the one you don't care about to find the correct equation. In this case, this is going to be my equation. So I write that equation. I'm going to be looking for you to write that equation. V equals AT plus VO. You're going to get credit for writing that equation, so make sure that you do. So real quickly, the things that I will be looking for, grading you on. Did you fill this out correctly? Did you interpret the problem correctly? Because they're not always going to just flat out tell you every number. This one's easy, they kind of do, but they may not. You may have to read into the situation, know some physics to fill this out. So did you list those out and fill them out correctly? Did you pick your equation correctly? Now we plug in, watching for signs and so forth. Now once again, this is a simpler problem, so it shouldn't be too much of a problem to do this. Actually, what I want you to do next is solve this thing for t. So solve for your target variable first. That's another thing I'm looking for. So we're going to go v minus vo equals at. Subtract vo from both sides. Then we're going to divide both sides by a. So I got v minus vo divided by a equals t. So t equals v minus vo over a. Now, that's another thing I'm looking for. So let's just make that clear. Did you solve for the correct variable? Then, lastly, and probably least importantly, is plugging in to get your answer. So t equals my final velocity, which is 49 meters per second, minus my initial, which is 39 meters per second, divided by my acceleration, which is 3.84 meters per second squared. And let's see, 49 minus 39 plus 10, divided by 3.84, 2.6. So the time it takes to do that is 2.6 seconds. Check. Notice that even though you're going faster, your change in velocity is still an increase in 10, the same way it is from here to here. So then you could go through all that for the next problem, but you'd get the same answer, because the only thing it would, this difference, right, let me put it right here, would still be 10, right? It would be 79 minus 69 or whatever. What is it? Yeah, which is still 10. All right, so let's look at another one. Let's see, where is it? There's one. Okay. So we're going to do a problem with an emu. I mean, let's face it. Physics is awesome. You get to do problems involving emus. So, first step. You should probably pause the video, do the first step. Because otherwise you watch me do it, you're not going to get it. I'm great at it. I know I'm great at it because they pay me for it. But you're the one learning it, so you got it right now. While I'm yapping on about this, you should be writing down the first step. What are you doing? Hopefully, what you've done is you've written XO, original velocity, acceleration, final position, final velocity, and time. That was the first step. One. Boom. Boom. Step one. Done. Then we go in and we read the problem. We try to make sense of the things that they give us and in the situation and fill in as many of these as we can. So an Australian emu is running due north. I think in their text they assume that to be a positive direction. In a straight line at a speed of 13 meters per second. All right. So that's the initial speed. And then he slows down to a later speed. So I know the initial speed is a positive 13 meters per second. And he slows down, still headed in that northern direction, but he slows down to a velocity later on of 9.5 meters per second. I say he. I really don't know the gender of our emu. So I may later on, just for fairness' sake, say it's a female. In a time of, time. How do I know that's time? They don't say time. Oh, come on. They give us a unit of seconds, right? So seconds is time. So it takes 2.5 seconds for that change to occur. Notice I'm putting units every chance I get. Always a good idea to do that. So what is the magnitude and the direction of the bird's acceleration? Now I'm hoping that you can tell me the direction already. But we're going to see how the math, if we pay attention to things and do things the way that the equations tell us to, how the math can help us out here. Now, once again, I'm going to say we're going to start at 0 meters. So the thing they want is the acceleration, and once again, the thing I don't care about is x. So once again, no and no. I'm going to use this one again. Don't worry, we'll get to some where we get to do those as well. So I write down that equation. Notice, right? Step 2 was right here. Boom. Step 3, boom. Write your equation. Now solve for your variable, which is in this case acceleration. So step 4 is going to be, let's see, I'm going to rewrite this as AT plus VO equals V. Just switch the sides. And then I'm going to have AT equals V minus VO. Divide both sides by T. A equals V minus VO divided by T, which you recognize is the formula for acceleration, which is all this is, just reworked anyway. That's step 3. Bam, step 3 taken care of. Now, plug in for step 4. I got the acceleration is going to be V, which is 9.5 meters per second, minus the original, which is 13 meters per second, over 2.5 seconds. Now, if you're a sharp cookie, you've already noticed, hey, wait a second, Wellborn, this right here, hold on. You're like, wait a second, this is going to come out negative. What? If you're a sharp cookie, you know why, right? You know why? Because if we said his velocity was positive, and he slows down, his acceleration has to be in the other direction. And the opposite positive, because we're only doing one-dimensional motion, so it's just positive, negative, that's it. So we got ourselves a negative acceleration when it's all said and done. I'll take care of the pushing of the buttons, although you should be ahead of me. 9.5 minus 13, you can handle that. It's negative 3.5 meters per second. Done. That change occurred in 2.5 seconds. I got an acceleration of negative 1.4 meters per second squared. Not surprising, got a negative acceleration. Okay, that's part A. But now we go to now we'll start with basically like a whole new problem for part B. We're going to keep this acceleration because the acceleration remains the same. So here's what I would suggest. In fact, I'm going to do this. Boom. We're going to clone this page. Boom. And I'm going to get rid of everything I just did. Except the acceleration that I just found out, because we maintain that. So I'm going to remind myself up here that the acceleration is still negative 1.4 meters per second squared. Then I'm going to start all over again. I got XO, VO, acceleration, final X, final velocity, Wellborn, final velocity, and time. Now, here's the interesting part. This is where the reading of the problem becomes. We're now, we've done the first part of the problem, was from when he was going 13 meters per second to some spot where he was going 9.5 meters per second. Now he's going to keep going, and we want at some time later, at an additional 1.3 seconds. So from here, so actually for me, I'm going to start the whole problem as if this is my t equals 0, and this is t equals 1.3. I could care less about this section. I'm going to deal with this second part. So his original position, I'm going to call that 0, because I can. Why not? And when I'm done, if I find x, I would know how far he went, but I don't think it's going to matter, because I don't think they want that. So I start 0. Now, original velocity, see, is 9.5 meters per second now, because I'm just considering this second phase of his motion. The acceleration is negative 1.4 meters per second squared. Negative. Don't forget that. Final position, I don't know it. They don't give it to me, so I think that's going to be my unknown again. Final velocity, I think that's what they want. What is the bird's velocity? So after that is 1.3 seconds. Ooh, 1.3 seconds. So I'm starting a whole new problem in that second part of the motion. So I don't care about x. So once again, yet again, I'm going to use the same equation. And in this case, I'm solving for final velocity, so it's already solved. Well, that's not too bad at all. V equals negative 1.4 meters per second squared times 1.3 seconds plus his original velocity, which was 9.5 meters per second. And so So 1.3 seconds later, its velocity would be 7.68 or so, 7.7 meters per second. There we go. All right, in the next video, we'll deal with ones that we'll try to get into using these two equations as well and look at some free fall as well. So it's important you watch the next video as well.